Exponential functions, we've been dealing with exponentials, and now we're going to look at exponential functions and the form. Now, you know, we've done other functions this year. We've done linear functions, we've done quadratic functions, we've done higher polynomial functions. It'll be, you know, we remember all the curves and the zigzags and all that stuff. Exponential functions, we talked about, we kind of saw what they would look like in their last lesson, and the average rate of change. You kind of saw what they would look like, but in this lesson we're going to look at the actual equation of them. And in the standard form, you know that lines, when you do a line, y equals mx plus b, that's the standard form for a line. So I'm just going to write this down. You don't have to write this, but you know, a line would be y equals mx plus b. Okay, we know a parabola would be y equals ax squared plus bx plus c. Anything that looks like that would be a parabola. X minus h, and again, you don't need to write this down. X minus h squared plus y minus k squared equals r squared. That would be a circle. So we know standard forms, right? We've done this with other functions. Exponential, here is the standard form for exponential functions, and here's what the y, and here's the in function form, f of x equals. This is more proper. This is going to kind of be what, you know, you may see, but you know, y is the same thing, it acts the same way. Where a is the starting value, so whatever the starting value is for your exponential function, that's going to be a. B is the growth factor, like, is it doubling? Is it tripling? Is it multiplying by 4? What is it multiplying by? That's the growth factor. Think of that as a ratio. And then x would be the number of time periods that we're talking about. It doesn't have to be years. It could be weeks, days. You're going to see a couple different examples here. A lot of times it is years, but think of it as time periods. All right, so talk about the growth factor here. Our growth factor b will always be positive. More specifically, b is greater than 1. The function will increase or show growth. If b is between 0 and 1, the function will decrease or show decay. So if the b value, if we have b equal to 3, that means the function is going to go times 3 times 3 times 3. Here, if b equals 1/3, the starting value is going to keep dividing by 3, dividing by 3, dividing by 3. That means it's going to go smaller. So if I start off with $9,000 and it's 1/3, decreasing by 1/3 is going to be $6,000. Decreasing by another 1/3 is going to be, another 1/3 of that's going to be another $2,000. So you're going to keep decreasing when it's 1/3 or a fraction. So that's this right here. The growth would be there. The decay would be, that would be an example of decay. All right. So here's examples for each. For each of these, your science class, here we go, is collecting cans. You start with 150 cans, so that's the beginning value, that's your A. Your collection triples every week, that's your growth factor. So A is 150, just doing this on the side. A is 150, and my growth factor is 3. How many cans will you have collected after 7 weeks? So what we want to do is write an exponential function here. All right, so we're going to have f of x equals, now I need my A value, which is my starting value, 150. And then I need my growth factor, which is going to be, it's going to triple, so that's 3. And then how many cans will you have collected after 7 weeks? Well, that's the 7 weeks is the number of time periods. Now, are we talking about weeks and weeks? Triples every week, collected after 7 weeks. See how it's weeks and weeks? So that's okay. So it is going to be 7 time periods. Right? Time period is a week, 7 of those. All right, so there's going to be our equation. I'm sorry, the equation, I messed that up. Boy, okay. 150, that's part B. 3 to the x, number of weeks, right? Okay, so x weeks. And then here you're doing f of 7. F of 7, because it's 7 weeks, 7 time periods, 3 to the 7th. And that's going to come out to be 328,050 cans. Okay, so we only start off with 150, but then it's tripling. You're tripling every week. And after 7 triples, okay, it came out to be that many cans, 328,050 cans. A population of 2,500 triples in size every 10 years. What will the population be in 30 years? Now we got to think about this one a little bit. F of x equals, We're starting at 2,500. That's the easy part. My factor, my growth factor, because it is tripling, so my growth factor is 3. But my time, so it's going to be to the x, right? But x is 10 years. Okay, 10-year periods. I'm sorry. X is in 10-year periods. X is in 10-year periods because it triples every 10 years. So B is 3, but that's only every 10 years. For part B, I want to do f of what? Well, I want to find the population in 30 years. So how many time periods is that? Each time period is 10 years. It's tripling every 10 years. So how many 10-year time periods is it going to be? 30 years is how many 10-year time periods, if that makes any sense. So we're going to do f of 3 because it's 3 10-year time periods. So 2,500, 3 to the third, and that's going to be 67,000, and I did this ahead of time just to save time. You can just type this right in your calculator. 67,500 would be the population. You just put the population is 67,500. Okay, tripling every 10 years after 30 years, 67,500. A bacteria culture doubles in size every 8 years. All right, so let's see. F of x equals, the culture starts at 150 cells, so 150. It's doubling, so 2 is the growth factor, B is 2. And it's every 8 hours. So B is the growth factor, X is every 8 hours. Okay, every 8 hours is the time period where it's going to double. So this is to the X, all right? So now we have to say f of what? F of what? 150 times 2 to the what? Well, we want 72 hours. Now, we wouldn't put 72 here, guys, because it doesn't double every hour. It's every 8 hours it doubles. If it doubled every hour, we'd do 72, but it's doubling every 8 hours. So how many 8-hour periods is it going to be? 72 hours. How many 8-hour periods is 72 hours? Think about that. How many 8-hour periods is 72 hours? It's going to be 9. Okay, 8 times 9. 8 times 9 is 72. So 8-hour periods, we want to get to 72. We need to multiply by 9 of them. So there are 9 8-hour periods there. So we just throw that in our calculator, 2 to the 9th times 150, and that's going to be 76,800 cells. Okay, 76,800. Now, I skipped over the 24-hour one. So that was actually, there's actually 2 questions here. So this is after 72 hours. So this is after 72 hours. How about after 24 hours? After 24 hours, same, except f of what? Well, how many 8-hour periods is 24 hours? It's 3 8-hour periods. So you're doing f of 3, 2 to the third, and that's going to give you, I did this ahead of time, 1,200 cells. Okay, so we went from 150 cells. After 24 hours, it's 1,200 cells. After 72 hours, it would be 76,800 cells because you keep multiplying. Double, 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 double. All right. So now we're going to talk about percent increase and decrease. The formula is similar. We're going to use our exponential right here. But because we have a rate and it's in percents, which you're going to have to change to a decimal, our formula, our B value, B is actually 1 plus R, 1 plus the rate, or it's 1 minus the rate. So B is either going to be 1 plus R or 1 minus R, depending on increasing or decreasing. All right, you can't just use the growth factor, because it's not necessarily a growth factor, you have to use the percent, and it's 1 plus or 1 minus. So here's some examples. A 20% increase is 100% plus 20%. That's 120%. B is 1.2. For a 15% decrease, it's 100 minus 15%, 85%, 0.85. See how that works? So that's why we have to do, so for this one, we'd be doing that, and then for this one, we'd be doing that. Okay? So, and there's a 6.75% increase, 106.75%, 1.0675. You're going to see that as we go through here. So, an investment of $2,000 expects to earn 6% interest each year. So what's our equation going to look like? Our equation is going to be, so we're going to have f of x. So we're starting with 2,000. And is it, well, we're earning interest, so it's increasing. 1 plus the rate, 0.06. 6% is 0.06. You move the decimal 2 to the right. All right. To the x. That's going to be our function. And we'll just, you know what I'm going to do? I'm going to f of x equals 2,000, 1.06 to the x. Because you really wouldn't leave 1 plus 0.06. You'd write it as 1.06. So that's our function right here. And then part B wants us to use the function to answer the question, what will the value of the investment be after 15 years? So we're just going to plug 15 in for x. Pretty simple. F of 15. F of 15, 2,000. 1.06 raised to the 15th. And that I did in the calculator ahead of time. You do this first, exponent first, then multiply by 2,000. Write that down as a note here. Okay, raised to the 15th first, then multiply by 2,000. This 2,000 does not get raised to the 15th. And it comes out to be $4,793.12. So that's 6% interest, takes our $2,000 up to $4,793 in 15 years. Now, for part C, we want to use a table because, well, part C wanted us to graph the function on the calculator. I'm going to bring up the calculator here. And so you can see it. And I already did this ahead of time. You'd go to y equals. I typed it in just to save time. See, there's our, in your y equals there. You type it in 2,000 times 1.06 raised to the x. You're going to do this in class tomorrow for the group work. And go to your table, second graph. Okay, you can see the table. We're trying to find out when the investment will grow to exceed 7,500. Okay, so when will it reach that 7,500? So I got to keep scrolling down, 5,000, 6,000, up, there it is. When does it first reach 7? So here's 7,600 right there, and that's the 23rd year. Because at 22 years, it's only 7,200. It doesn't reach it yet. So 23, you got to go to 23 years. So 23 years, and that's just from the calculator. You might want to put a note there from the calculator. All right, and last one here. Pikesville had a population of 14,200, so f of x is going to be 14,200. Now this time, the population is decreasing. So I know it's going to be 1 minus the rate, 2.5%, that's 0.025. 2.5% is 0.025. Move the decimal 2 to the left, and it gives you the decimal version. All right, and that's to the x. And I'm just going to rewrite my function. 14,200. Growth factor is going to be 1 minus 0.025, which is 0.975 to the x. So there's my actual function right there. And then part B, f of what? Well, we start in 2014. We're ending in 2022. Okay, so how many years is that? It goes by how many years. You don't put 2022 in. You put the number of years. So it's 14 to 22. That's 8. So f of 8 is what we're doing here. 14,200, 0.975 to the 8th, because it's 8 years later. And that's going to give us 11,596. So you could see how the population decreased from 14,200 to 11,596. We'll call it people. Okay, 11,596 people after 8 years. if it's a 2.5% decrease each year. Go to the, now again, part C, just like up there, I'm not going to do it to waste time on the video. You're going to go to your table and scroll down and till you get after 10,000, and it took 14 years. I'm just going to give you that answer there. But again, it would be done the same way as we did part C in number 4. I just wanted to show you how part A and B really is different from the other one because it's a decrease.